So this is the last lecture of this module, and we're on Chapter 11, an introduction to Riemann integration. So it's a one-lecture chapter, which means that I'm going to be explaining the theory with some illustrative pictures, diagrams, examples. We won't have time to prove lots and lots of results. However, we will look at some examples in a bit of detail. And as it says here, it summarizes at the beginning of the chapter. There are some lemmas and theorems mentioned in this chapter, and you don't need to know how to prove them. You won't be asked how to prove those lemmas and theorems in the exam in January. But you will be supposed to know what those theorems say and to be able to apply them. You're supposed to know what the definitions say. You're supposed to be able to check examples and decide what sort of properties examples have got. So any examples we do today will be examinable. If you do look back at previous versions of the notes and previous exam papers, there was a slightly different approach in between 2003 and 2005, well, 2005 to 6. Riemann integration was done slightly differently using some things called step functions, but since then I've gone back to a more standard approach. So what is all the fuss about? Why is there an issue? Well, just as being careful about continuous functions and being careful about differentiating functions is important, turns out that you've got to be careful about integrating. You've been told forever that if you want to integrate a function, you will anti-differentiate it and then evaluate between two limits if you want to do a definite integral, and that will give you the area under the curve and that sort of thing. And you've been doing that for years. But there's a problem. Not every function can be anti-differentiated. There are plenty of perfectly reasonable functions around where there is no antiderivative, no function which, when you differentiate, gives that function. We're going to, there's some examples of that on the last question sheet. I'll mention some of them today. So if someone gives you a function, how do you know whether you can anti-differentiate it or not? Well, of course, you say, well, do the integral and then differentiate that and you'll get the function back. But that's not necessarily true. And in any case, what does the integral mean if you can't anti-differentiate the function? So that means as soon as you realize there's an issue and that there might be some functions that you can't anti-differentiate, where you can't find a function whose derivative gives you that, then you realize you're not quite sure what integration is going to mean. So, okay, you go back to the area under the curve version. You think you know what area under a curve means. But then, do you really know what area under the curve means? What if your function is 1 at the rationals and 0 at the irrationals? We'll be looking at that later. That's a really horrible function. Can you decide what the area under that curve is? So then maybe you don't know what the area under the curve means either. And in that case, what are you going to do? You can't anti-differentiate. You don't know what area means. Can you integrate or not? Well, that last function I mentioned is so horrible that you can't integrate it with the theory I'm going to tell you about today. But you can integrate it using a better theory called the theory of Lebesgue integration, which you would meet if you do more advanced analysis, and in probability theory, for example, as well. So some functions are too bad for the Riemann integration to handle, and then you go to Lebesgue integration, and then you have to go to really horrible functions such that you can't even prove they really exist unless you use something called the axiom of choice before the Lebesgue integral can't handle them. Okay, so what is an antiderivative for a function? If you've got a function little f, an antiderivative for it would be a function big F whose derivative was equal to little f. So you've got, say, some little f may be some real-valued function defined in an open interval, and you try to find a function big F whose derivative is that. And I've warned you that you can't always do it. Antiderivatives, they're also called primitives or indefinite integrals because, of course, indefinite integration. If you find one, you can add a constant to it, and you've got another one. So if you do find one, you've got an arbitrary constant of integration, or you get infinitely many antiderivatives for free. There is a sort of converse to that. The difference between any two antiderivatives must be constant on any interval it's defined on, because its derivative would be 0. So here's a useful set of functions, the characteristic function of a set. They're also called indicator functions. If you're doing probability, you might call this the indicator function of the set. And instead of writing chi sub e, you might write 1 sub e or something like that in probability theory. But the idea is it's a function which is 1 if you're in the set and naught otherwise. So that sounds reasonably harmless. If your set's fairly nice, that's not too bad. If your set's an interval, then it's going to be 1 when you're in the interval and naught elsewhere, so it'll be 0 most of the time, jump up to 1 when you're in the interval, jump down to 0 again elsewhere. The problem comes if your set is something unpleasant like the rational numbers. And it turns out that you even have a bit of trouble if your set has just got 1 point in it. So if your set E has just got 1 point in it, it turns out that your function has no antiderivative. And that's on sheet 5. That one could be integrated, but when you integrate it, you get 0. So, here's height 1. Here's your point. So you've got one point A, which is the only point in your set. Then your function goes along at height 0, suddenly jumps up, and then it jumps down again, and off it goes. So this is y equals chi e of x. Characteristic function of a single point set, it jumps up to 1 suddenly. Now, so what's the problem? You can integrate it. The area under that curve is 0. So if you try to anti-differentiate it using integration, you would try the constant function 0 as your antiderivative. Unfortunately, the derivative of the constant function 0 is 0, which is the wrong thing. So when you integrate this and differentiate again, you don't get back to where you started. So that's the first problem. So here's a function. You have to work harder to prove it's got no antiderivative, but that's the first problem, okay? And characteristic function of the rationals is much worse than that because it jumps up and down between 0 and 1 all the time. And not only is it no antiderivative, that one's got no antiderivative, but you also can't use Riemann integration to integrate it either. So there's the first issue. However, I think the best result that comes out of this chapter is that continuous functions are okay. If you've got a continuous function, you can always anti-differentiate it. You do it by integration, area under the curve approach, and it's okay and it works. But as soon as you realize there are issues, it becomes unobvious that continuous functions are okay. Remember, continuous functions can be pretty horrid, but continuous functions do turn out to be okay, and that's the first fundamental theorem of calculus, which comes near the end of this lecture. So continuous functions are okay, you can anti-differentiate them. However, there are also some discontinuous functions that you can anti-differentiate. Equivalently, can you find a differentiable function whose derivative is discontinuous? So you're looking for discontinuous f and differentiable capital F with f prime equals f. That's a tricky exercise. If you haven't seen it in calculus, you may well not be able to think of an example. Of course, if you've seen it before, then you just read off your standard example if you've met one. So you can have a differentiable function whose derivative is discontinuous, in which case you've got a function with an antiderivative, and yet it's a discontinuous function. But generally, most functions you meet around when you're trying to do applications, you generally work with nice functions. Your nice functions are normally continuous. That means that you can antidifferentiate them using the theory in this chapter. Any questions about antiderivatives? Obviously, I haven't proved the claims I made so far, but there is some stuff on it on the question sheet 5 with some more details in. So now we've got to try to develop our theory of Riemann integration. Now, Riemann integration is all about trying to estimate area under curves by using rectangles. And what you do is you approximate your function from above and below. You draw the graph of your function, and you fit rectangles below it and rectangles above it, and both of those give you an estimate of the area. And so you get an estimate, and you get an overestimate by doing rectangles that are just above the curve. Okay, I'm assuming that we're dealing with a non-negative function for the moment, so that area is in the positive sense. So let's assume you've got a non-negative function. You estimate the function from above using rectangles and from below using rectangles, and then you're going to get an overestimate for the area and an underestimate for the area, and then you ask, are those estimates close to each other? If they're very, very close to each other, then perhaps you've got a good estimate for the area. If you're dealing with something like the characteristic function of the rationals, it's hopeless, because the rectangles under the curve are going to be much lower down than the rectangles over the curve. So we're going to be talking, we're only going to try and integrate bounded functions. This theory only covers bounded functions. If you want to do unbounded functions, you can go to improper integration, which was dealt with in last year in analytical and computational foundations. There was a bit about improper integrals, I think, maybe something in calculus as well. So if you want to do improper integrals, you can handle some unbounded functions too. But for the moment, we're just going to work with bounded functions. A bounded function defined on a closed and bounded interval, AB. And we're going to be chopping up our interval into finitely many pieces in order to do our estimate using rectangles from below and from above. These estimates, so when we split up the interval into finitely many pieces, we'll be talking about partitions of the interval. When we do these estimates using rectangles to try and estimate the area from below and above, we're going to call those Riemann upper sums. They're the overestimates where the rectangles go just over the curve. And the Riemann lower sums are going to be where you estimate the area with rectangles just below the curve. You don't expect to get an exact answer by doing one of these Riemann sums, which is going to be the estimates using rectangles. But you hope that you're going to be able to get very close to the answer. So first of all, what's a partition? It's just a finite set of points, x0, x1 up to xn, but there are some restrictions here. N must be at least 1, so n's a natural number. So there's a trivial partition where you just take the left-hand endpoint and the right-hand endpoint, and it's not a very exciting partition. Otherwise, you probably have a few more points than that. The x0 has to be at the left point, A. Xn has to be at the right point, B. The other ones fit somewhere in between. So we're talking about something like this. Here's A, here's B, and that's x0 is here. xn is here, and then you've got finally many other points maybe in between. x1 up to xn minus 1, but xn must be at b, and x0 must be at a. And that's your partition. So obviously there's infinitely many possible partitions, and each different partition is going to give us a different set of rectangles to approximate the function with. And if you want names for those x0 up to xn, we're calling them the vertices of the partition. And now you've got your function f and you've got a partition P. So you've got a bounded function f on this interval, and you've got your partition. You divided it up into finely many pieces, but as above, so same restrictions as before. So x0 is less than x1, so on, less than xn. x0 is at a, xn is at b. And now, let's look at one rectangle, estimating the function. So you can look at the interval between xk minus 1 and xk. This works where 1 is less equal to k less equal to n. So I'm going to look at one thin rectangle between 2 points of the partition. So here's xk minus 1. Here's xk. And here's y equals f of x, which could do all sorts of things. Well, we're working on this interval here, so we just working between xk minus 1 and xk inclusive. And you say, how high does it go? It looks like it goes to about that high. So here's mk of pf. F is a function, p is a partition, k is which interval are you looking at the moment. And then on the underneath, here's the little mk of pf. So you estimate your function from above and from below as closely as you can on that little interval. Now, as you can see, we could use that to estimate a little bit of area. So you could do a little rectangle below the function. Here I'm assuming the function is non-negative. Of course, you don't have to, and this definition works anyway. So I've shaded in red a lower estimate for the area under the function between xk minus 1 and xk. But you can add a bit of extra area on top to get the upper estimate, but if I do that, it's going to hide the function. So I won't actually shade the other bit. But you can see that now you've got a little rectangle that closely fits the function from below, and another one that closely fits the function from above. And you hope, and it doesn't always work, you hope that that will give you a decent estimate for what the area under this function might be. It's unfortunate that it doesn't always work. But this is what you try, and this is how you define, this is one bit of defining a Riemann lower sum, Riemann upper sum. Okay, so that does one bit. Now what do? You do it on all of those intervals and you add them up to get your estimates from below and estimates from above. So now we sum over k. There are n intervals, so we sum from k equals 1 up to n. That mk of pf, that's the height of the upper line. xk minus 1, that's the width. That's the width of the kth interval. So you can see you're now getting the area of that rectangle based on the kth interval, the overestimate one. And then you add them up, and you get your overestimate based on areas of rectangles. There you are again, width for the kth interval. And this time, you're using your lower estimate. So you're probably estimating the area under the function from below. So U is for Riemann upper sum, L is for Riemann lower sum, and each of these estimates the area. And let me draw you an example then with, say, 4 pieces in it, or maybe even 3 pieces in it. You might have something looking a bit like this. So here we are, I've got one with 3 intervals here. I'll draw a fairly random function. And now let's see what's going on with this one. Well, I have to put some vertical lines up. And now I've got to do the little m's and the big M's. So I've got to estimate from above and from below. Well, so on the first interval, that's going to do, that's M1 of PF. So again, P equals X0, X1, X2, X3 here. And I'm drawing you just a sample picture. This doesn't prove anything. It's just to give you an idea of what's going on. Again, I want to just closely fit it from below. So this is going to be the little m2. And on the third one, I'll just fit it closely from below, and I'm going to get little m3. But I also want some estimates from above. So I'm going to have to get the closely fitting rectangle from above, which comes to here. That's capital M1 PF. And the next one is slightly higher. Always difficult to get a good picture out of this. So that one there is M2 of PF. And where's M3 is probably about, actually it's probably about, it looks like M3 is the same as little m2. So it looks like the biggest f got in my third interval was the same as the smallest f got in the second interval, which can happen. And now you do your estimates from above and below. And our lower Riemann sum for this one, L of PF, is the total shaded area. It's the estimate from below, using rectangles, as closely fitting to the function as possible. And of course, the upper one, U of PF, would be the corresponding area but using the rectangles fitting F from above. But again, I won't shade that because that will... so that's a corresponding overestimate using the upper rectangles. Any questions about partitions, lower sums, upper sums? So we're just trying to estimate the area under the curve. Well, okay, I'm drawing a non-negative function, but you can do exactly the same thing, and the formulae are the same throughout. Even if the function goes negative, you use the same formulae I've given. You still end up estimating from below and from above in the same way, using L and U. P is a partition, F is a function. For every partition, to every function and to every partition, you get a corresponding lower Riemann sum and upper Riemann sum. But you can't allow unbounded functions because otherwise these things can go infinite, and we can't work with infinity. Well, it's blatantly obvious that the lower sum is less or equal to the upper sum. But that's if you take the same partition. What's a bit harder to prove, and you can find the details in books, is that if you take a lower sum corresponding to one partition, but an upper sum corresponding to a different partition, you still get the right inequality. So what's this? If you had the same partition, it's obvious that the lower sum is less or equal to the upper sum. But if you take different partitions, how do you know you can't find two really weird partitions, one where the lower sum manages to get above the upper sum for the other? Well, you can't. You wouldn't expect that to happen, and it really can't happen. The way it works, actually, is if you take a partition and refine it by adding in more vertices, then it turns out that the lower sum can only get bigger and the upper sum can only get smaller. So if you do take two different partitions, you can put all the vertices together and get a better partition than both. The lower sum can only go up, the upper sum can only go down, and then your inequality follows from that. But you don't need to know that proof. What you need to know is that it doesn't matter which partitions you take, P and Q, the lower sum corresponding to P can never go bigger than the upper sum corresponding to Q, even if they're different partitions. Any questions about that? Right. So now we're nearly in a position to talk about integration. You've got lots of lower sums for your function, you've got lots of upper sums for the function, and all of the lower sums are less or equal to all of the upper sums. What that allows you to do is to take the supremum of all the lower sums and call it something, and you can take the infimum of all the upper sums and call it something. So you could take the least upper bound of all the lower sums, and you could take the greatest lower bound of all the upper sums. And those two might not be the same, unfortunately. And also, you don't expect to find a perfect match with some rectangles, but by the time you take the least upper bound of the lower sums, that probably won't be the same as any of them. You don't expect to find a maximum lower estimate, because you expect the lower estimates are getting better and better the thinner the rectangles you take. So you probably won't find a maximum lower estimate, but you can find a least upper bound for the lower estimates, And that, you hope, will be a good estimate for your integral. And similarly, you can look at all the upper estimates, the estimates from above, the upper sums. You probably won't find a best set of rectangles to take. But you hope that the thinner the rectangles you take, the closer and closer your upper estimates get. And so you can take the greatest lower bound, the infimum of all the upper estimates, and you hope that's a good estimate for your integral. And if those two estimates are equal, you say you've found an integral. So this is the definition of the Riemann lower integral. Note that bar underneath it to show it's the lower integral. And here's the Riemann upper integral. Note the bar on top of it, which tells you that it's the Riemann upper integral. The Riemann lower integral is the estimate from below. You look at all the different partitions, and they all give you these lower Riemann sums, estimating the thing from below. You look at all these estimates from below, and you take the supremum, and you call that the Riemann lower integral, which is about the best you could do from below using rectangles, but you take the supremum of all those estimates. And the Riemann upper integral is about the same. You look at all the different partitions of AB, call them Q. For each of them, you get an estimate from above, U of QF, using rectangles. You don't expect to find a best possible estimate, but you can take the infimum of them all, and you get the Riemann upper integral, with that bar there showing that it's the Riemann upper integral. And now you've got two different numbers, the Riemann lower integral and the Riemann upper integral for the function over the interval. And the question is, are they the same? And the answer is sometimes yes, sometimes no. Any questions on the definitions of the lower integral or the upper integral? You think of it as doing the best you can from below. Okay, you may not find an exact best, but you just take the supremum. You do the best you can from above. You may not find an exact, actual, best possible partition. So the best you could do is take the infimum of all the numbers you get that way. And if they are equal, then we say it's Riemann integrable. So a Riemann integral function is one where when you do your supremum of estimates from below, you get the same as the infimum of estimates from above. So if the Riemann lower integral is equal to the Riemann upper integral, then we say it's Riemann integrable, and we define the Riemann integral to be the value equal to them, and you get this. And now, this is our notation for the Riemann integral. So if you see an integral sign coming later in this section, it means that you're dealing with an integrable function, a Riemann integrable function, and we're taking the Riemann integral. And we hope we've now got a really good estimate for area. But you can't integrate unbounded functions this way because some of those overestimates or underestimates would go infinite, and then we're in trouble. So we don't even try to estimate unbounded functions using the Riemann integral, but you can use what's called improper integrals, and that was as you had a bit of that last year. So you can find out more about improper integrals. We won't talk about improper integrals in this chapter. Any questions about what it means for a function to be Riemann integrable? Let's move on. There's a whole pile of theory about this that would take lectures and lectures and lectures and lectures to prove. But fortunately for you, I'm just going to tell you the answers, and you don't need to know the proofs. The Riemann lower integral is always less than equal to the Riemann upper integral. That's because all of the lower sums are less than equal to all of the upper sums, and that remains true when you take the supremum of the lower sums and the infimum of the upper sums. Every Riemann lower sum is less equal to the lower integral because the lower integral is the supremum of the Riemann lower sums. Every Riemann upper sum is greater than or equal to the upper integral because the upper integral is the greatest lower bound of the Riemann upper sums. I'll draw a little sketch to show you why constant functions are Riemann integrable. When you take a constant function on an interval, all of the rectangular estimates are exact. So suppose you've got a constant function. I'll point out what's going on with these integrals. Actually, before we lose it, let me note that, as I said, there are an awful lot of Riemann integral functions, but we're going to see in a moment that there are some bad ones around. So your function is constant. Let's make it a non-negative constant just to make life easy. Well, if your integral wasn't c times a minus b and b minus a, there'd be something strange going on. Well, it doesn't matter how many points you divide into, your rectangular estimates from above and below are always exact. So what happens, and you can check the details, for all partitions P, you get mk of Pf, both of the mk's are equal to c, which is, of course, the infimum and the supremum of the values on any of the subintervals. So that's for 1 small equal to k small equal to n. P is, as usual, x naught up to xn. And u of Pf equals L of Pf is always equal to c times b minus a. So, since they're all the same, by the time you take the infimum or the supremum, they stay the same. So you get the lower integral it's the same as the upper integral. Is still c times b minus a. Thus, f is Riemann integrable. If the lower integral equals the upper integral, then it's Riemann integrable. And the integral is the same as both the lower and the upper integrals. So without the bar, you can just say it's equal to c times b minus a as well. So that's the Riemann integral. Okay, so that's the easiest possible example of a constant function. If the constant function didn't work, there'd be something wrong with your integration theory. Now, it will turn out that there are quite a lot of functions that you can integrate this way, but there are some which you can't. Anyone need more time on that slide? Yeah, okay. So it's going to turn out that every continuous function is okay, but it's going to turn out that the characteristic function of the rationals isn't. The characteristic function of the rationals has this problem that it goes jumping up and down between 0 and 1 in a sort of dense way. All the lower rectangles are distance 1 below all the upper rectangles, and it becomes hopeless. So let me just draw you a picture of that, which will involve drawing some dots. So what does a graph of the characteristic function of the rationals look like? Well, it's hopeless, but let me just draw some dotted lines. Let's have a vertical line here. Well, it also has dotted line all the way along the x-axis as well. Because it jumps up and down, both Q and Q complement are dense in R. So no matter where you look, there's points nearby as close as you like to you where you're rational, and other points as close as you like to you where you're irrational. And so the best you can do is these dotted lines on the top of the bottom. It keeps jumping up and down horribly between 0 and 1. As a result of that, here, for every partition of 0, 1, every partition P of 0, 1, all the little mk's are 0. All the big mk's, estimating from above, are 1. As a result, all the LPFs are 0. All the UPFs are 1. So by the time you take the least upper bound of the lower sums, you still get 0. Which is not equal to 1, which is the upper integral. And since the Riemann lower integral is different from the Riemann upper integral, it's not Riemann integrable. So since the Riemann lower and upper integrals are different here, F is not Riemann integrable. Any questions about that example? It's quite a nasty function. In this module, that's just about the nastiest function you meet. On the other hand, when you do more advanced theory like Lebesgue integration, this turns out to be a very easy function because it turns out that there are far fewer rationals than there are irrationals, because there's only countably many rationals, whereas there's uncountably many irrationals. So in fact, although you saw these two dotted lines, It turns out that it's 1 far less often than it's 0. So by the time you do Lebesgue integration, you can integrate this function and you get the answer 0. So Lebesgue integration is better, but Riemann integration can't handle it. Okay, so here's some standard facts which we don't have a chance of proving. Every continuous real-valued function on a closed and bounded interval is Riemann integrable. Well, what this is saying is that something nice about being continuous means that those estimates from below and the estimates from above are really close to each other if you take thin rectangles. Now, it's not as obvious as you think. You have to go through a bit of advanced theory involving some stuff called uniform continuity, which we haven't done. Uniform continuity will come up in third year. But we haven't had time to talk about uniform continuity. It's a slightly better kind of continuity, but it's rather nice thing is that if you have a continuous function on a closed and bounded interval, you get uniform continuity for free. It's not obvious, it's a theorem. And then from that, you can really prove that these lower estimates and the upper estimates get very close if your rectangles are thin enough. And it's so close that you can prove that the thing's Riemann integrable. Bit of theory to look in books if you're interested. You're allowed to quote this. Every continuous function on a closed and bounded interval is Riemann integrable. And Riemann integration has all the properties you would hope for from an integral. What's that? The integral of a sum is the sum of the integrals. If it didn't do that, then there'd be something wrong with your theory. But it's not obvious that if you add two Riemann integrable functions, you're still Riemann integrable. It's a bit of theory that we don't have time to do. Constant times a function is rather easier, actually. You could probably do that one just from the definitions I've given you without doing much work. So you can prove that a constant, if you've got a Riemann integrable function and you multiply by a constant, it's still Riemann integrable, and you get what you expect, constant times the integral. If you've got a function f less equal to a function g, and they're both integrable, then you get the usual estimate on the integrals. Remember, a is less than b here. Here's an interesting one. The modulus of the integral is less than or equal to the integral of the modulus. That's a genuine inequality. You don't expect to get equality there unless the function keeps the same sign. Otherwise, you get some cancellation. If you've got bits of the function above the axis and bits of the function below the axis, then they cancel out and when you integrate, and the modulus doesn't add. Whereas the one on the right-hand side, the modulus does add, and you count all area positive for that one. So the inequality is strict, usually, when the function changes sign. And for part E, this is saying that integrals add up, areas add up the way you expect. I can draw you a quick picture of that one. Oh, sorry, I've run out of room. I want A, B, and C. Oh, no, that's okay. I want C in between A and B for some reason. So this is your function f defined on A, B, and C is somewhere in between. Well, you've got these two different areas. Informally speaking, this is what you think is going on. So the first shaded one is the integral from A to C. The second shaded one is the integral from C to B. And you do hope that they add up to give you the integral from A to B. And fortunately, it turns out that with Riemann integration theory, this does work. And that brings us on to the last two theorems of the chapter. The first one is the fundamental theorem of calculus. You were told it in first year, but it's actually a rather difficult, tricky theorem about Riemann integration of continuous functions. But it tells you what you already knew. If you take a continuous function defined on your closed interval AB, and now you look at defining the integral from out to x of f of t dt, which is the sort of thing you did last year in calculus, then you hope that when you differentiate this, you get the function little f back again. And the answer is yes, you do. With the way we worked in this module, you work on the open interval. So now you know that Riemann integration can act as anti-differentiation if you do it this way, integral up to x. So if you go and check all the details of the proofs in the books, you will really know that what you were told in first year is true. So I won't say anything more about that. Just to finish, the final result is a mean value theorem of integral calculus This says that you can estimate an integral of a continuous function. Doesn't work if it may not work if your function is discontinuous. But as long as you've got a continuous function, you will be able to estimate the integral using it'll actually be equal to the function value somewhere in between a and b times the width of the interval. So this is the same as saying that f of x naught, of course, is 1 over b minus a times the integral from a to b of f of x dx. That's the average value, or the mean value. So for a continuous function, there will be an x naught between a and b where the value is equal to the average value in this way. And that's the mean value theorem of integral calculus. So they're the two big theorems from this chapter. The fundamental theorem of calculus is a really important one because it tells you how to that you can anti-differentiate continuous functions. I think that's more than enough, and all remains me to wish you a good holiday. If you do have questions, feel free to send me an email. Good luck in the exam.